I want to talk about an experiment that I made earlier this year, where I wanted to teach myself how to use a library called sundials. So we've had interfaces to the sundials library for a while now. And so sundials is a library that originally was written to solve complicated ODEs. And as part of this, it implements implicit time-stepping methods. And when you have implicit time-stepping methods, you need to solve nonlinear equations, systems of nonlinear equations, so that you can solve nonlinear implicit ODEs. And it has a subpackage. Sundials has a subpackage that is called Kinsol, K-I-N-S-O-L, that implements these sort of nonlinear solvers. And I wanted to teach myself how this works. And so what I wanted to do is to revisit step 15. So step 15 is the first nonlinear solver problem that we have. It solves the minimal surface equation. And there are a number of deficiencies in step 15 where we know you could do things better. And I wanted to see how easy or how difficult it would be to do it right with Sundial's Kinsol package. And it turns out it's actually quite simple. So what I'm going to do is I'm going to walk you through what the issues are with step 15 and how we address this. So let me share my screen here. So back here, let's close this, make this full screen. So because that's what I do, I wrote this talk in the form of the slides that I have for these video lectures, because eventually this will become a video lecture, namely 31.61. It needs to fit into the existing numbering scheme, of course. So in step 15, what we want to do is we want to solve this sort of equation here. So minus divergence, some constant and material parameter, gradient u over square root of 1 plus gradient u squared equals f. And it's pretty obviously nonlinear. And the way we think of nonlinear problems is that we bring everything to one side. We call this the residual, and we want it to be equal to 0. And you've all seen how Newton's method works. So if you want to solve R of u equals 0, then Newton's method would say, well, you need to have the derivative, R prime times the update equals minus the residual. And then you compute uk plus 1 equals uk plus delta uk. Or if you want to be on the safe side, you're going to add a what's called the step length, alpha k, in here. So step 15 does this, but not particularly well, or let's say there are some open questions. So the first one is, what is the variational formulation of this problem here? So we need to come up with a weak form of this for the finite element method, and it turns out to be not so trivial to actually get to it. And I'll show you how this R prime looks like, and you will understand why maybe we don't want to compute it by hand. Then the second issue that we have to address somehow is how do we compute this alpha k, this step length here? So step 15 just says pick 0.1 in a convergence, but that's not efficient. We know how to do better. We know that we need to choose it differently in each iteration. And so an extension of step 15 is, well, how do you actually do this? And then it turns out that so assembling this matrix here, that's actually quite expensive. And maybe there are ways to make this cheaper. So I'm going to walk you through the ideas that are behind this program that I wrote, and that is step 77. So the variation of formulation that you can find in step 15 already. So it looks like this. It's not so trivial. So the derivative of the residual, which we call the Jacobian, is this sort of matrix here, or this operator. That's a test function. That's the update, the delta that we compute in each step. And then it involves the old solution uk in here. And so there's two terms, And so and the residual itself looks like this after integration by parts. So in each Newton step, we have to solve this sort of equation for delta UK, which appears here and which appears here. And you see, it requires a little bit of calculation. And if the problem was any more complicated, then doing this would be, well, let's say annoying. So there's another tutorial program that I'm not going to talk about. It's called Step-77 that computes this automatically, where you basically just have to provide a description of what R of U is, and it's going to automatically compute the Jacobian matrix by using a technique that's called automatic differentiation or symbolic differentiation. That was written by Jean-Paul Pelteret, and that's also part of this upcoming 9.3 release. So I'm going to just take that for granted that we know what's the derivative this Jacobian matrix is. But the questions that I do want to address is, so we know that in Newton's method, where if you didn't have this alpha k here, where you just compute the new update as UK plus delta UK, we know that does not always converge. You have to start close enough to the solution for it to converge. And in order to make it always converge from any starting point, you need to do something that is called globalization. Globalization means that you can start anywhere on the globe, globally, right? And the way this is typically done is that you choose this alpha k here in such a way that UK plus 1 is better than UK. And we would have to define what better actually means, but the point is that the algorithms that we use for this are typically called line search. So this Newton step, this delta UK is computed from these equations. So in essence, what that says is, I want to go in this direction, delta UK. And then I have to ask the question, well, how far do I want to go in this direction? That's this alpha k. And so that's I have to ask a question about, well, what happens along this one line? I have to search for a place along this one line. And so that's where that term line search comes from. Step 15 does not do this. Step 15 just says set alpha k equals to 0.1. Step 15 doesn't do it because it's actually quite difficult to implement this. So the algorithms that are used for line search are not trivial. And there's probably a couple hundred lines, not trivial, I mean, a couple hundred lines of code, but awkward stuff. There's a class in deal.II whose name I've forgotten just now that helps with this, but step 15 doesn't do it. The other part is if you think about having to solve this linear system, this Newton update system here for delta UK, you can make the following case. So if you're still far away from the solution, maybe it doesn't really matter whether we can find the exact direction for the Newton step. Maybe it's good enough if we, sort of have the right direction, right? And the point being that I know that I'm far away from the solution. It doesn't really matter that I go to the exact Newton direction because it's not going to get me to the exact solution anyway. I will have to do more Newton steps after this. So you could compute, for example, these Newton updates on a coarse mesh. That's what step 15 does. But you could also solve the linear system inaccurately. So maybe we don't need to solve the linear system to very high accuracy with very small tolerances, but you could do it only inaccurately, right? And if you look at what big practical codes for real problems do, that's exactly what they do. They solve the initial updates on a coarse mesh and only gradually make the mesh finer, but then they also solve the linear system inaccurately. So there are strategies that tell you how accurately you have to solve the linear system. The most widely used is called it's the Eisenstadt-Walker trick. Eisenstadt-Walker trick says, well, you have to solve the linear system to this particular accuracy, and it gives you a rule of how accurately you need to be. But step 15 also doesn't do this. And the other part of this is, since we already concluded that maybe we don't need to compute the updates particularly accurately, maybe maybe it's also not necessary that we compute the Jacobian matrix at each step. Assembling a matrix is expensive. And in particular, it becomes expensive if you want to have really good preconditioners. So if you had a preconditioner for, let's say, an algebraic multigrid, it's expensive to set these up. And maybe we can get away with not computing the matrix in every step and the preconditioner in every step, but only doing it every once in a while. So again, you need some sort of rule that tells you how often you have to do this, maybe every 5th iteration, or maybe every 7th, or maybe every 2nd. So there needs to be some criterion that it decides whether you want to recompute the Jacobian and update the preconditioner. And that's also what big practical codes really do, but step 15 does not. So the goal for this Step-77 program that I set for myself is that I would like to have a program that does optimal step lengths via line search, and only updates the Jacobian matrix in the preconditioner when necessary, and if possible, also solves the linear system inaccurately with a tolerance that makes sense. So Step-77 actually only does the first 2 of these. You will see how the third one could be done. I didn't do that because I just used a direct solver. So a direct solver happens to be the best preconditioner, if you want, right? That computes the exact decomposition of the matrix. And so that's a very expensive step, of course, right? So if you don't want to do this in every iteration, if you can get away with it, you compute the matrix and its sparse decomposition as rarely as you can. But of course, if you do have a direct solver, then there is no tolerance with the linear systems anymore, right? So that's why I don't solve the system inexactly. I just apply the sparse decomposition, and so my tolerance is always 0 in this case. So the question is, how do you do this, right? This is clearly going to take a lot of code. So I'm thinking this might be many hundreds, maybe a couple thousand lines of code. And the answer to these sort of problems is, like, well, you're using deal.II, that's because you don't want to reinvent the wheel, right? Other people have already written all of the finite element functionality you ever want in deal.II. Similarly, the solution to using advanced nonlinear solvers is to use packages that other people have already written, and Kinsol, as part of Sundial, is one of these. There are others. I should also point out that both PETSI and Trilinos, for example, have modules for the nonlinear solution of linear systems that are probably, for all practical purposes, quite equivalent to Kinsol. But Kinsol has a good reputation in the community, as does Sundial. And so, since we already had interfaces to this, I thought I'd give them a try. And so what I want to do for the next few minutes, not a lot, is to walk you really quickly through how Kinsol actually does this. So Kinsol is written by a bunch of people on the West Coast in the Bay Area at Lawrence Livermore National Lab, who over the last, I don't know, 2 or 3 or 4 years, have really put a lot of thought into how a good user interface would look like. What is it that this library needs from a user, from us, to solve nonlinear systems efficiently? And then, so Kinsol is written in C, and then Luca Heltai and his group in Italy have come up with really very nice ways of wrapping this sort of interface in C++. And you will see how super elegant it is. So it's, I really like what everybody has contributed to this. It's a pleasure to work with this. So, so this is step 77. It's in the usual tutorial program format. And what I'm going to do is basically just show you the code for 5 minutes. So very quickly, but so the idea of this program, I'm removing all of the commentary that's in there, is, I mean, it looks like step 15, which looks like step 6. There's really nothing fancy to it. The point, though, is this. if you only compute the Jacobian matrix every few Newton iterations, then you need to separate the functions that compute the residual, the right-hand side, and the function that computes the matrix. And in my case, because I want to use a direct solver, I also need to factorize the Jacobian. So there are two key functions here that usually would be in this one assemble system function, but are now separate, namely the computation of the residual and the computation and factorization of the Jacobian. And then the rest of it, of course, happens in this run function. And so in this run function, that's sort of where I would like to start my my investigation here. So we have this, you do a bunch of setup here, and then you have a loop over mesh refinement cycles. Okay, so we want to start on a coarse mesh and then make it gradually finer. And the important part in here is really just this block here. That's the key piece. My mouse doesn't quite reach all the way down to here. Let's do it again. This here, this is fundamentally the part that drives Kinsol. And so to walk you through this really quickly in the remaining 3 minutes, so I'm setting up this Kinsol object here, okay? And then Kinsol needs to know just 3 or 4 pieces of information. So one of those is it needs to create auxiliary vectors for its internal working. So the way Luca and his colleagues wrapped this goes like this. So this nonlinear solver, this Kinsol object here, has a member variable that is called reinit vector that is a function object. And so you can think of this as a callback. So this is a function object that Kinsol calls whenever it needs to create and reinitialize a vector. This function object, I can tie to it a lambda function. So a lambda function is a local function, an unnamed function. In this case, it takes a vector and it wants me to resize this vector as appropriately. And that's exactly what I do here. Okay, so I create a local lambda function that Kinsol can call back into. That's one of the 4 pieces. The second piece that we need to address is that Kinsol needs to call user space to compute the residual. The residual is this f of u. So I need to know what is this u, that's the input, that's what Kinsol gives me. And I put the output into this residual vector. And so I create a lambda function that takes these 2 things as arguments and calls compute residual. That's my user function that computes the residual. That in essence builds that's the same thing as building the right-hand side in step 15. And then Kinsol wants to know whether it succeeded or not. So yeah, it succeeded. I returned 0. There's nothing that can go wrong. Then every once in a while, we want to rebuild the Jacobian matrix. And so there is another member function, member variable of this nonlinear solver object that is called setup Jacobian. And it's going to give you the current solution. It's also going to give you the current right-hand side, which in our case, I don't actually need. And my lambda function that I create here simply calls the member function compute and factorize Jacobian. Okay. And the last thing that Kinsol is going to need is how do you solve a linear system with the Jacobian matrix? So that's what it needs to do in every Newton iteration. So this is this member variable here, also a function object, solve with Jacobian. It gets as arguments the right-hand side. It gets as a second argument the output. That's where the solution of the linear system is going to be put in. And then it takes as a last argument the tolerance. So that is the tolerance with which I have to solve this linear system. And this is what the Eisenstadt-Walker trick tells us we need to decrease over time. And so I'm going to call my solve function, right? And that's really all there is to it with the tolerance. And I don't really want to look into what solve does here. It just applies the direct solver. But the point is that if it was an iterative solver, it would have to solve a linear system to a given tolerance. And then after setting up these four things, I just call nonlinear solver.solve, starting at the current solution. And it's going to compute the solution to a given nonlinear tolerance that I set up here, the target tolerance, okay? And it's going to call compute residual as often as it needs. It's going to update the Jacobian matrix as often as it needs, and it all works automatically. So I don't have to implement a line search. It's really all very elegant. And so at the very end here of my presentation, let me really quickly, about a solution, show you how this looks like in practice. So on the first mesh refinement, my target tolerance is 0.1. So it computes the residual. So it probably wants to know, this is all, the logic is driven by Kinsol, and I'm just outputting information from my own function. So it computes the residual because it wants to know what the starting residual is. It asks me to compute the Jacobian matrix, and then I factorize it, and then it asks me to solve a linear system. And then these are probably line search steps where it computes the residual that corresponds to UK plus alpha k delta UK for different values of alpha. Apparently it's happy after the second step, and then it asks me with the new solution to solve another linear system. And you notice that it didn't ask me to update Jacobian matrix here. Okay. As a matter of fact, the next time this happens is only down here, right? So there's like a half a dozen Newton iterations where it does not require the update of the Jacobian matrix, right? And all of this is happening automatically. And eventually I'm happy with it. It has reached the target tolerance 0.01. And I do one mesh refinement step and decrease the target tolerance, and we repeat this whole cycle. But the point is that if you add it up over this first cycle here, it assembles the Jacobian only twice, but computes 61 right-hand sides, and does 19 linear solves. So only twice out of these 19 linear solves does it actually require me to update the Jacobian matrix. And I think this is all really elegant. And if you look at this program, it has approximately the same number of lines as step 15, but is vastly more efficient. So this is a good place to stop. The program is online. You can find whatever you want to look at. I highly recommend using Sundal as a good library.